All right, so we're gonna talk about how the sun is powered, because not only is this interesting in terms of technology, but it also really sealed the well, I'd say it's primarily interesting because of technology. That's the way that our human brains work. We always want to make things easier for ourselves. And we're very much interested in the next energy solution here on Earth. And we talked about this a bunch in the last class. But it also tells us about how people came up with this idea of the structure of the sun. Because obviously you can't look down into the sun, right? You can only see what you can capture from the surface. We basically have light, and that's it. We have some other magnetic information, and we have some pictures of what's happening at the pseudo-surface of the sun, right? So remember, the consensus picture is that the sun doesn't actually have a surface, which is perplexing. But the idea is that there's essentially a level at which the light is emitted. We call that the photosphere. And there's been this long history of debate, and I went into depth, and I read you some of the words of the people who were working on that debate at the end of last class. I want to continue with that a little bit because the story comes to a conclusion today. What's really interesting is that pretty much all of this work that set the stage for everything we know about the sun was accomplished about 100 years ago. So the story wraps up today with Einstein, the special theory of relativity, and Addington, who was a great popularizer of Einstein. It's hard to really explain how important Addington was in this saga, because Einstein was a German. Germans were not popular in the West around the time of Einstein. Nobody spoke German in our country, certainly in England. There was a great divide. And so Addington was a British astrophysicist who really found a way to popularize Einstein's ideas. And so that kind of plays into why we even care about Einstein in the first place. And we'll talk about that a bit. Some people have been asked, especially when we had our first coffee hour last week, a lot of people are really interested in the questions of general relativity. I had told some of you that we would deal with it today. Looking at the syllabus, it makes more sense to deal with that when we get to black holes and all of that spooky stuff. So I'm going to hold off on general relativity. I will touch on special relativity today, but this is not the class for special relativity. You're going to have to take a more advanced physics class to really get into that. But we'll deal with the most important parts, because special relativity is what really allowed us to conceive of this idea that the sun powered itself through fusion. And Addington and some others played a big role in putting those pieces together and coming up with the picture that we have today. So remember, just a quick review of last time. We talked a lot about how people were desperately struggling to come up with a story for what caused the sun to have the appearance that it did, in particular, its spectrum, right? And that's what happens when you put a prism up and you look at the different kind of light that comes out of it. And there was all sorts of debate, right? Because the central crux of the problem is that the sun gives a continuous rainbow from the photosphere, which is marked by lots of gas lines. And there's these sunspots. People didn't know what they were. They were trying to make sense of it. There are these dark holes. They look like dark holes in the surface of the photosphere anyways. And so, the question of how the sun is made played into this. The question of how a gas could be opaque plays into this. And there was a lot of confusion and argument about that, and it really went on all the way into the 20th century, and the argument wasn't finalized until this final battle between these two astronomers, Arthur Addington and James Jeans, who were both prominent British astrophysicists. And the rivalry was insane. It was like, I don't know, pick your favorite sports team, like OSU, Michigan. I'm from Ohio, so Ohio State, Michigan. It's like more important than anything at Ohio State, right? Like, I worked in a lab there after college for a little bit, and it was like the whole campus shut down when there was an Ohio State-Michigan game. I mean, it was much more important than any of the research, much more important than than the academics. It was just absolutely at the center stage. These guys, I don't want to say they hated each other. I think Jeans probably hated Addington, and I'm going to read you some quotes from him that I'll let him put it in his own words. But needless to say, Addington won that battle in the end, for better or for worse. He certainly had a lot of good ideas, and we'll talk about how that unraveled. But what we are left with today is this idea that the sun is actually the solution to it's really quite interesting. So, is the sun made out of gas? Is it made out of liquid? The solution's a hilarious compromise because now we say the sun is made out of plasma. Well, what is plasma? It's like a little bit of both, right? So that's kind of interesting. I'm sorry? It is kind of whatever you want, right? And the more you study it, the more you realize that. And I found a really interesting paper that's come out recently by a prominent plasma chemist who is essentially saying that, hey, it actually might make more sense for us to treat this type of plasma as a liquid. And so the whole argument's kind of gone full circle. Jeans gets defeated by Addington with the gaseous sun, but today we're kind of creeping back towards this liquidous model. Of course, there's more to it than that, and I'm hoping that we'll have time by the end of class to read you some of their ideas in their own words. But first, let's deal with the standard, the contemporary interpretation for how the sun is powered and how we came to understand, like what went into that, because this is the paradigm that's held since the Eddington-Jeans debate, which was it was about exactly 100 years ago today. So we've been stuck with one paradigm for about 100 years. It's on the move, but it's really important that you guys understand what that consensus paradigm is right now. It's the one that's printed in your textbook, and so I want to go over it. And certainly, just like with all paradigm shifts in science, we don't just throw out the old ideas, we integrate them and build them into something new. And I think that's probably what's going to happen with the sun and with fusion. So the ideas we'll go through right now concerning fusion are absolutely going to be embedded in whatever comes next. The more valid way of looking at this is probably that there are different ways that fusion can happen. And so there's some exceptional stars that we're starting to find out there that don't quite fit into this narrative. And I'll hopefully talk about one of those at the very end, which is a really fascinating story. So, we'll play with that story a bit more today. And then next time, we'll do the next chapter, which is basically about spectroscopy and understanding stars in general and how we can know different things about them just by looking at the light. A couple of students emailed me also. I was telling a story about my cat last time, so I said I'd show a picture of my cat. So there's my cat. Yeah. She's a bit of a writer. No. Okay, so one thing that people really started to realize in the 1800s was that they started building machines for the first time. This was like the real birth of the industrial age, right? And one of the first things that all of the experimentalists who were working on machines and providing the theory to the engineers that were building these massive, mostly steam engines actually, one of the first things that they realized, although there had been whispers of it for some time, was that energy was a conserved property. And this is important when we start to think about what energy is, which we'll get to in a minute, because it's not so clear. However, Helmholtz, Lord Kelvin, these were great thermodynamicists. These are people who concerned themselves with how heat was transferred in and out of systems, because that's how you make a more efficient machine, right? That's how you make a more efficient engine. You have to make sure that you don't lose unnecessary heat energy, essentially, right? Because heat's just one form of energy, and we'll play with that in a second. So Kelvin and Helmholtz, both working on these engines, I think that's a better word than machine, I guess, engines, working on engines, they championed this idea, the contractile idea of the stars, right? It's particularly our sun, how it formed. which is pretty simple. Gravity squeezes it, it gets hot, and it lets off a bunch of heat. Now, this isn't a bad idea. Actually, this is pretty much how we think about how substars like Jupiter, or perhaps you've, perhaps you've heard the term brown dwarf, right? Which is essentially a Jupiter-like star, not a star, sorry, planet. These things actually do seem to heat themselves by squeezing gravitationally. And this is probably really important in the way that stars form initially. There's a bit more to that, and hopefully we'll have a chance to get into star formation at some point. But these guys were championing this idea. The problem is that if you just ascribe the gravitational contractile process to heat, and that's how the stars are powered, the problem is that the sun turns out to not be old enough, right? So let's see here. It's something like the amount of energy that you can get out of that is something like 10 to the 42nd joules. By the way, what this means when I say something like 10 to the 42nd, this just means a 1 with 42 zeros after it, right? So this is just shorthand. This is called scientific notation. This is what we use so we don't have to just say like 10 gazillion or whatever it is. It gets really confusing. So when I say that, I'm just talking about enormous quantities. So the problem is that it's putting out something like 10 to the 26 joules per second. So that means that you only have about 100 million years worth of energy in the sun if you squeeze it. So this didn't work out. And these guys kind of threw in the towel on it. Problem is that left this enormous chasm where all of a sudden nobody had any idea how the sun generated its enormous power. And there was a huge vacuum there for a while people were sorting it out. Darwin became really popular at this time, and I think this is a huge part of the reason that people turned their back on this idea of the contractile star, because Darwin was saying that these organisms, like ourselves, evolved over hundreds and hundreds of millions of years, and so how could it be that we had time for that if the sun was only around for 100 million years? And these things Darwin was, it's hard to explain how popular that idea became in the intellectual circles towards the end of the 19th century. It just wasn't a tenable proposition. So what was it? And so that kind of brings us up to Einstein, Jeans, Addington, all of these guys. But actually, it was one of the fundamental physicists who really first proposed the idea that something in the nature of nuclear science could be involved. Actually, Ernst Rutherford, who's very well known for the characterization of the electron and some of the very early particle chemistry, particle physics, proposed that maybe it was radioactive decay that was responsible for this. And so that became pretty popular. However, it eventually became, and actually Jeans was a huge proponent of this idea. The problem was people started to realize that the sun was made almost entirely out of hydrogen and helium. So that didn't make sense. So they had to look for a new mechanism for that. Now, all of a sudden, this guy, so there's some sort of interesting things happen. So all of a sudden, this guy Einstein appears on the scene, right? Well, it wasn't quite like that. So why in the world was Einstein such a famous monster of science? It's not as simple as just this guy bursting onto the scene with a good idea. This takes us back to the story of the luminiferous ether, okay? Now, what's really interesting is that for almost the entire history of rational science, so people actually trying to come up with mechanistic explanations for what's happening, everyone had assumed that things like light and magnetism were conveyed by a medium, right? There was something in between the objects, like the flashlight and your face, that was conducting that light signal, right? This was just a foregone conclusion because how in the heck do you make sense of it otherwise, right? And there's other things that fed into that too. You know, people realized that light had a definite speed to it, which makes perfect sense if you have a medium. You know, if I if I make a wave inside of this table, it's going to travel at a characteristic speed which reflects the properties of this material. And that's going to be the same for everything, right? There's the speed of sound in air, right? It's consistent, assuming the air has constant density and so forth. So everybody who came up with everything that we know, essentially Maxwell's equations, everything that describes how electricity and light behave, every single one of them assumed some sort of ether, they called it the ether, was responsible for conveying these signals. Now, the problem was they couldn't find it. And they looked really, really hard. People were designing all these ingenious experiments to find some evidence that there was some medium present. And most of these experiments went something like, well, we'll shine a light on a mirror, and the reflection should come back at a slightly different angle and speed because, of course, the Earth's moving through the ether. And so the light signal should be like slightly incongruent with where it left from. Excuse me. Now, this is unfortunate because in my own estimation, I think the way that things went wrong here is that people assumed that the ether was a separate substance from the actual atoms themselves, right? And one thing that I'm realizing in my own research is that the atom, if we look at the atom, and we'll play with the atom here in a minute, the atom, if you look at it, is mostly defined by its outer surface, which we call the electron. Actually, the electron's a really, really dirty word because it's not always treated like an object. It's sometimes treated like an activity, and the confusion there has gotten out of control. But if you look at the equations that give us the shape of the atom, and we'll look at some of those shapes in a minute, what you find is that there's the actual surface of the atom, the electron shell, extends indefinitely, right? You actually have a very small chance of, if you go and probe the atom and say, where's the surface of it? There's a very small chance that the atoms in my body will be found at the back of the room, okay? This is really weird, but what it says to me is that that substance that people were looking for outside of the atoms was the wrong approach, because actually, if the atoms themselves are carrying that substance with it, in other words, if the substance is the atoms themselves, then when the Earth moves, the ether moves with it. And so you're never going to be able to detect something external to the bodies themselves. So people didn't have that insight at the time, and what happened was, instead of pushing through and trying to understand a conception of the atom that would allow them to rectify this, unfortunately, they said, hey, what if we just forget about it? What if we just don't worry about it and we try to explain the interactions of matter based on their perspectives with respect to one another? This is called relativity, essentially. And I talked about this a little bit with the idea of the magician and the lady getting sawed in half last time, right? Now, it works really, really, really well is the thing. You can absolutely describe interactions in nature by putting them in a relativistic perspective. It's very, very effective. It's very, very descriptively powerful. The problem was that, in my estimation, that this really pushed the physicists out of the picture and brought the mathematicians into science for the first time. Math became king in science for the absolute first time, because prior to the death of the ether, math was seen as useful in terms of recognizing patterns that were occurring in nature. And certainly the engineers welcomed math because they were able to fine-tune their engines and so forth. But it wasn't seen as the fundamental structure of the universe. Today you have people, you have guys like Brian Greene or Susskind. You have people saying that actually math is at the center of what's happening. And in effect, there are laws of the universe, and everything is basically following those laws. I don't know if there's supposed to be a little law police out there making sure the atoms do their job and stuff, but the idea is that math is at the center of everything. So this was a huge paradigm shift that happened at the beginning of the 20th century. And Einstein rode in on that wave a little bit. In fact, there was a very competitive theory called Lorentz relativity, which actually did assume a medium that was somewhat kinetic, like that which I'm describing, which is actually just as valid as Einstein's relativity, but people didn't want to mess with it. They couldn't find this substance, and they didn't want to have a substance that they couldn't find in their theories, which it's like, fair enough. But I think that this has led to a whole host of problems down the road, and especially when we get into cosmology towards the end of this semester, it's going to become apparent that math can give us all sorts of interesting illusions which might not be true. You know, a great example, I'm not sure if I mentioned it last time, probably, but a great example is heat, right? You know, at the same time all of this was going on, people in the 1800s treated heat as if it was a fluid substance that flowed from one body to the next. This is perfectly mathematically valid. It works perfectly. The equations for the flow of this caloric fluid are perfect. They work out. They'll allow you to build engines and stuff. Problem is, it turns out to be absolutely wrong, right? We now know that heat has to do with the vibration of atoms and molecules, right? And so Einstein was actually, he actually had the fortune of working in a lab during grad school where he was able to do some very foundational work about the way that actually heat manifested itself in atoms. Perhaps you've heard the term Brownian motion, which is just kind of referred to as this random wiggle. This is what Einstein did his preliminary work on. And he also had the opportunity later to do some work on the photoelectric effect, which is essentially how it is that, you know, light can actually excite a charge inside of a system. And this is what he ended up winning the Nobel Prize for. A lot of people think he won the Nobel Prize for relativity or something to do with space-time. Not true, right? So Einstein was a very, very, very effective engineer and mathematician long before he got famous for any of this relativity business. That helps a lot, actually, right? If you've done something super practical, people are going to start paying attention. And Einstein was also a really good team player, right? He made friends with people all over the continent. Actually, most of his math came from a dude named Minkowski, who helped him develop the complex calculus necessary to complete his theories of relativity. So it's really important to understand the times, the constellation of the social environment that allowed him to come up with this idea, which terminates in this concept today, at least, of defining what energy actually is, particularly energy in a static substance, right? So we're going to play with that. I don't want to say anything else about this. Let's get back to, so we'll come back to the structure of the sun in a moment, but let's talk right now about energy, because I think it's one of the most abused words in all of science. And that's really important. It's probably one of the most abused words in the entire universe, because people will say everything from, you know, I'm feeling energized, to I can sense your energy, to whatever, right? And what do they mean? What does it mean, right? And I think that what's really telling is that, you know, even your textbook seems to have no definite answer to that. I'm going to actually read you a little quote from your textbook. It goes like this. Energy is a challenging concept to grasp because it exists in so many different forms that it defies any simple explanation. In many ways, comprehending energy is like comprehending wealth. There are very different forms of wealth, and they follow different rules, depending on if they are the stock market, real estate, a collection of old comic books, great piles of cash, or one of the many other ways to make and lose money. It is easier to discuss one or two forms of wealth or energy than to discuss the concept in general. I very much disagree with that, and I'm very, very concerned that this has made its way out into general textbooks and parlance. I think this is really, really scary, actually. Because energy is at the basis of almost all of the theoretical work that came to us in the 20th century, particularly with the way that stars work. And if we don't even know what that word means, what are we doing, right? This is bad. Okay, so let's try to figure out what that word means. So the Greeks actually were the first people to use this word. I wrote it up there in Greek at the top, which essentially says energia, right? Which means activity. And I think that's a good starting point. So this was in the 4th century BC. One thing that absolutely blows my mind constantly when I'm going through these topics is how so many of our ideas were established thousands of years ago, and we took this long, meandering path, and we try on every other possibility, and then eventually, many times, we come back and we say, you know what? They were right about that, actually. Okay, so let's see. What does Wikipedia say? Wikipedia says, energy is the quantitative property that is transferred to a body or a physical system, recognized in the performance of work. Okay, so this is really, really critical in understanding how we define energy today. So it does seem to be something that concerns the effort that's put into some sort of activity, right? We're quantifying the effort that's put in. And we'll get back to work in a second. But some of the first people to really work on the concept of energy, well, let's start with Leibniz, all right? So Leibniz championed this idea of this concept called vis viva. This is Latin. And what it means is something like living force or living strength or living power, right? It's some sort of ineffable quality that fuels everything, right? So what's kind of fascinating is that vis viva was essentially what we consider energy today. And they had pretty well characterized vis viva as being something equivalent to the mass of a system times the velocity squared, which should bring us pretty close to Einstein's E equals mc squared business that we're working towards, right? Now, people fought about this for a long time, but it was more or less accepted. So everybody from Newton to many of the fathers of electromagnetism, Huygens is one of my favorite all-time bosses of science. They all used this relationship, vis viva, to describe energy. Actually, the first person to use the word energy and resurrect it from the Greeks was Thomas Young, and that was, I think, maybe early, like 1805 or something, very early in the 1800s. And Thomas Young, of course, was really important in giving us the wave, a lot of the wave equations and dynamics that we associate with light today. He was also very active in elasticity. Young's modulus describes the stiffness of a material. Anyways, the word energy is pretty new in terms of the modern usage, right? So before the 1800s, you would have found it in a textbook called vis viva, but it was essentially the same thing. The modern, it's usually written, I'm not sure if it's written in your textbook, but the modern equivalent is called kinetic energy. And the interesting thing about kinetic energy is that it is essentially the equation for vis viva. They just stick a 1/2 in front of it. Now, I tried desperately to understand where this 1/2 came from. And it comes down to the equation for work. By convention, we've described work as a force applied to a distance, right? And so in order to get the balance between work and kinetic energy to work out, you have to put this 1/2 in front of it. But it's not necessarily true. It just needs to be there in order for all of the equations to match up to one another so that we don't get lost when we're trying to tally the conservation of energy. You could easily say work equals 2 times the force distance, and as long as your conventions were proper and you use this 2 in all of your other equations, you'd be fine too. It's a little bit puzzling because it's true that it does take some sort of force to accelerate, acceleration's inside of the force, but it takes some sort of effort to accelerate a body to some sort of speed. But the distance thing is a little bit puzzling because in all honesty, if you're out in outer space and you apply a force to an object, it doesn't matter how much distance you cover, right? It really doesn't. It's going to keep going no matter what until something stops it. So this is a little bit perplexing. I know this is probably not that interesting to you guys, but the idea sometimes that in order to make all of your theories, your mathematical theories consistent, you need to introduce factors which are essentially there just to keep things in line, right? They're not necessarily reflecting what's actually happening. And this is just a little tail of the dragon from which mathematics can sometimes lead us down into strange places. Because if you start thinking that mathematics is actually what's happening, you're going to start to run into problems, right? It's much more useful, in my own opinion, to look at what's happening, maybe describe what's happening with mathematics, but never lose sight of the fact that physical reality is unfolding for the simple reason that objects bump into each other or pull on each other, right? If you go back to Newton's original work where he actually introduces this word force for the first time, he says something really nice. He says, he defines a force, actually it takes about a paragraph because he's just got this flowery language. And he's like, look, a force is a push or a pull. That's it, right? So I think this was the last time that people were so materialistic about these ideas, but it's a little bit tragic that it's gotten lost in that sense. So at any rate, Newton used this concept, vis viva. Coriolis modified it to this 1/2. Now, let's get back to Einstein. So, I'm going to read you another little quote from your textbook. Albert Einstein, when he developed his theory of relativity, is that matter can be considered a form of energy too, and can be converted into energy. Furthermore, energy can also be converted into matter. This seems to contradict what humans had learned over thousands of years by studying nature. Matter is something we can see and touch, whereas energy is something objects have when they do things like move or heat up. The idea that matter or energy can be converted into each other seemed as outrageous as saying you could accelerate a car by turning the bumper into more speed, or that you could create a bigger front seat by slowing down your car. And right, I totally agree with that. I totally agree with that. So what went wrong there, right? Is Albert Einstein's equation, which we have no time or interest in deriving for you right now, it does turn out to be perfectly valid. Is it telling us that matter can be converted into energy, or is it actually just defining energy, right? I would argue the latter, that it's actually defining what energy is for us, right? And what it's saying, if you look at the equation, did I even put it on the board? I did. All right, it's a very simple equation, right? It's telling us that energy means something is moving at some particular speed. This is essentially what the vis viva we're saying. It's some sort of material that's in motion. Energy always means a material in motion, no matter what we're talking about. Of course, you could have potential energy, right? This spring has the potential to go into motion, right? It has some potential, right? We squeeze it, and we know it has some potential, right? And we can qualify that by its material properties and so forth. But I think that the real secret here is, and your textbook basically shows the confusion here. Matter is something that we can see or touch. Now, I would completely disagree with that. So what matter actually is stuff that's made out of atoms is the thing. This is where things got off the rails, in my opinion, because matter is always defined in terms of mass. What is mass? Well, prior to the electromagnetic conversions that allowed us to make statements about the mass of an electron and so forth, which are all done with magnets, right? Deflection of something. Well, it has a certain weight, so it's going to be deflected this amount. Prior to that, the concept of mass, when it was introduced by Newton, always referred to something in a gravitational field. It always referred to something that atoms were doing to one another, right? So this idea that matter can be converted into energy is an interesting idea, but the idea that material itself can be converted into energy is a very misleading idea. So if we take this equation to say that energy means material in motion, well, that's a great definition of energy. If we treat the M as response as meaning atoms, then of course it is telling us that atoms can be converted into energy. But what is energy? It's some sort of material in motion. What does that mean? It means atoms can be broken down or combined into a new form of material in motion. And the hitch to that is that we can get a little bit of juice out of them when those conversions happen, right? And this is at the heart of all nuclear science today. that when you combine atoms and when you tear them apart, there is a bit of motion that's released into the system, and often a conversion of the form of material, right? I'm not going to say necessarily the conversion of the form of matter, because there's other pieces of material that we wouldn't necessarily consider matter. But in this sense, today, when we're talking about the fusion reactions in the sun, we're talking about atoms getting combined into new atoms. And when they do that, there's a little bit of motion that's released into the system. And that motion is what we talk about as the energy balance that's released. This is often treated as the binding energy, or something that we can get back. This is what's powering the sun, is this idea that when you squeeze atoms together, there's actually a relaxation that happens. You squeeze them together at the heart of the sun under extraordinary temperatures and pressures, and they form a new one, right? They're kind of like bubbles. They kind of come together, and the whole system relaxes a little bit. And so the evidence of that relaxation is in the form of heat. It's in the form of radiation predominantly. That's the one that we're most sensitive to here on Earth. That's what we're seeing, right? We're getting radiation. We're seeing light. Okay, so any questions about that? I know this is a complete whirlwind. Yeah.
Say we get energy from burning wood, right? Let's say I'm chopping wood, on a microscopic level, those teeny little splinters that I can't see as they're flying away on that piece of wood, they also are giving off energy.
Yeah. And in that sense, yeah, there's these conversion processes. What you're talking about is the conservation of energy, right? And this was really well known because, remember, these people are trying to hone these steam engines, right? They don't want to lose money. They don't have to pay for more coal than they need, right? It's all about the dollar for these people, ultimately, at the end of the day. And so one of the first things they figured out was that energy was not being lost, right? For whatever reason, and this is actually one of the most astounding pieces of the whole universe, is that the universe appears to have a fixed amount of energy in it. What does that mean? It means the motion of the universe ain't going anywhere. And it kind of makes sense if you think about it. Like, if we define the universe as everything that there is, including all of the motion that it has, where's it going to go? Something's going to crash into something. Well, it's got to keep going with all of that effort. If it's a closed system, there's nowhere for that extra effort to go. If there was maybe another universe touching us or something, well, I guess then it would just be part of our universe, right? It'd just be a bigger universe, right? So this conservation principle is at the heart of everything. And yeah, with most reactions, mechanical reactions, we're dealing with heat for the most part. Nuclear reactions are the only time that we're talking about this particular form of atomic rearrangement that results in this binding energy being dumped back into the system. And so this realization, which was in some sense elucidated by Einstein's revelation of E equals mc squared, which honestly, it's a beautiful little equation. I just hope that you realize the one thing I want you to take away from this is that it wasn't exactly a new idea. I think that Einstein was able to derive it out of relativity because he was looking for it to some extent. This is the equation for vis viva. This is an idea that goes back 500 years before Einstein. And so people knew from their own experimentation that energy was conserved and that energy could be described by this essential relationship between the velocity squared and the mass. So this particular form of energy is a static energy, right? This is the amount of energy available in a substance without having to move it around at all, right? This is not kinetic energy. This is just the definition for a material's inherent energy, right? And now what happened was people developed this into the idea of nuclear science. They developed it into the concept. The chemists played in on this. Everybody understood that, okay, there's some sort of, the atoms, even if you take an atom and you hold it perfectly still, there's still some sort of energy in it, right? It's still moving within itself. The substance that the atom is forged from, which is not really something that we play with today, unfortunately, but the fiber of the atom itself is in motion at all times, and that system, when you bust it apart or you squeeze them together, you get something back out of it, right? You can actually harness that motion of the atom itself. That's what fusion is all about. That's what fission is all about too. So that's also something you guys should probably be aware of if you're not already. Fission is when you break atoms apart. Fusion is when you squeeze them together. All of the scary nuclear technologies on Earth today concern fission. These are actually decaying, rapidly chain reacting reactions where these where these atoms are busting apart in various ways. Okay. Any more questions about energy before we move on to atoms? All right, cool. I hope that this is illuminating to some people anyways. Maybe you can go and tell your friends they have no idea what energy is. Okay, so this was huge. Everybody jumped on it. Everybody piled on it. E equals mc squared opened up the idea that, oh my goodness, atoms themselves inherently, not even chemical reactions, but atoms contain energy which can be released. All of a sudden, we have a mechanism for how the stars can be powered. All right, this was absolutely enormous, and it feeds into our discussion of the composition of the sun and the phase state of the sun, and we'll get back to that. But in order to understand exactly the reactions, the fusion reactions that are happening in the sun, I think that it's worth talking just a moment more about the structure of the atom. I've sort of played with it already, but I'll show you some pictures. So the atom, quantum mechanics was coming into its day at this time too. It was really becoming the most effective way of describing the way that atoms behaved. And essentially, the way that quantum mechanics treats atoms is that they are these pulsating objects, right? They can be described almost perfectly with a wave equation, right? So there's sort of like a ripple on a pond that's self-sustaining, if you can imagine that, or a drum, right? They are pulsing in this interesting way. And what's cool about that is that you can use the equations for spherical harmonics and pull out the shapes of these atoms. And it turns out that these equations actually work really well with every test that we can throw at them for describing what the atom looks like and actually telling us what the different surfaces look like. So it turns out that this is the periodic table, essentially, which you've probably seen. Oh, there used to be one here. I think it's behind the screen. So all of the elements, if you move across this, you start at the top left with hydrogen. It's a very, very simple surface atom, right? This is the shell of the atom. We call it the electron shell. It's a sphere, right? It's the most simple pulsation imaginable, right? And it's just vibrating, right? It has this energy to it. If you move across, what happens is when you start to get into the more interesting atoms, you get into the metals, right? You start to see the appearance of not only what we would say are additional orbitals, additional electrons get added to these. You probably heard this in chemistry class. But they take on new shapes, right? They have higher energy to them. And all this means is that if you take this substance that's vibrating like this and you put more juice into it, it contorts into new shapes and you get new surfaces, right? So all of these atoms, as you move down the periodic table, they also contain the earlier shells in them as well. But these atoms now start to present multiple surfaces, right? And the cool thing about these surfaces is that there's something about the motion of the material in those surfaces which allows them to entwine with one another, right? And we call this chemical bonding. And it introduces this concept of charge, right? Because there's something about the particular motion of those surfaces which gives it that attractive quality. And it has to be commensurate with another atom's particular surface motion in order for them to bind. We call this positive and negative charge. Now, this is sort of lost on people for the most part. Generally speaking, again, owing to the mathematical takeover of physics at the beginning of the 20th century, the concept of charge as plus and minus attractive forces was sufficient. People were like, cool, that works. Atoms, atomic surfaces, whatever, they have plus and minus surfaces. They're attractive. Good enough. Well, but what does that actually mean? What is go ask any of your, call up Neil deGrasse Tyson and ask him what charge means. Nobody knows. It's very, very interesting, right? I think this is actually going to be, I think there's a whole field of science that's going to open up that concerns the actual physical interpretations of what is happening on these atoms at the time, because something's happening. There's some sort of motion of that surface. There's some sort of frictional engagement of those surfaces on a positive versus a negative that allows them to twist together and actually stick, right? So, you know, this is a chart that comes out of your textbook, and you know, they list some of the relevant particles, is what they call them, and they list some characteristics about them, including their charge and including their mass. Now, what the heck is a particle? What do you guys think a particle is? Anybody? Yeah.
Actually, I have a question.
Oh.
What did the figures on the previous slide mean?
Oh, those are the shapes of the outermost orbitals, the surfaces of the atoms. They're derived from the wave equation, the Schrodinger wave equation for the electron at those different energy levels. And they tell us the shape of the atom, basically. Particles, anybody? Yeah, just give it a shot. But just like, what's your intuition? What's a particle? Yeah, how about you? You haven't talked to.
I've always thought about particles as small groupings of atoms, but I'm assuming from this chart it's smaller than that.
Smaller than that, right? So anybody else? Particles? We're talking about like subatomic particles here, like the electron and the proton. Anybody, you know, you guys have probably seen this in chemistry class in high school or something. What the heck is a particle? Yeah. Yeah, that's generally how it's taught, exactly. It's the building blocks of an atom, right? And were that so, our lives would be so much easier. The problem is that a particle is actually a mathematical concept that essentially tells us that there's some sort of event that's happening here which can be quantified in a vector coordinate system. So it's some quantity that changes with respect to time at a particular location. And the particles can be predicted, right? We know exactly how they change with respect to time. We know what can be measured here, and we can predict what will be measured later. So take the electron, or the proton, or the neutron. These are very predictable events that can be detected given some established original circumstances, right? So it's kind of unfortunate that we call them particles instead of events, because of course calling them particles makes us think like they're a speck of dust or something like that. In reality, a particle is actually an abstraction. It's a dynamic thing. It's something in motion. It's really an event, okay? So can you build a desk out of events? It's a little tricky. Yeah?
Doesn't string theory suggest that each particle is a vibrating band?
It does. But the problem is, the problem is that string theory is, when you ask what a string is, it's actually a one-dimensional entity, right? And this starts to take us out of the material world very quickly. So it's actually a series of symmetries that are present between the motions of materials, right? Now, a lot of people don't like string theory for lots of reasons. Most people don't like string theory because it's untestable. The predictions it makes can never be solidified as true or false, right? It's below the level of it. The statements it makes are beyond the reach of empirical observation. So a lot of people hate it for that reason. I hate it. I don't hate it, but I have trouble with it because I think that those abstractions, while potentially useful, again, they take us away from the material explanations that I think are desperately necessary in order to move our technology forward, right? If we keep treating things as if they're made out of activities, it confuses our minds. It confuses the students. It confuses the people who need to take our civilization to the next level. Look, guys, we're burning stuff still to keep our lights on. This is some caveman stuff, right? We need to move past that. We need to harness the power of the sun. If we're going to be able to do that, we need to be very clear with ourselves about what the materials are doing in order to pull off that magic, right? It's not sufficient to say, well, there's some events crashing into other events. In my estimation, this is a terrible, terrible mistake that's happened, And it will be solved. This is absolutely something that will be solved. I don't know if it's going to take 10 years, 5 years, 100 years, 1,000 years. I guarantee you the aliens have solved it if there's aliens, right? It is not possible for people to comprehend, well, aside from some small portion of mathematically minded people, it is not useful to conceive of physical phenomena in terms of abstractions interacting with other abstractions. It just starts off the rails, and then it just goes completely into the ditch. Yeah?
So are particles not physical objects?
That's right. Yeah. So if you learn one thing today, well, hopefully you're going to learn a couple of mind-bending things, but that's another one. A particle is not a physical material body. And this is very troublesome. So, you know, the chemists actually are some of the most sane scientists that are out there. They kind of realized this from the beginning because the chemists, from the very beginning of molecular theory, essentially once people, you know, we had atomism since the Greeks, but the chemists from the very beginning realized that the shapes, the structures of the chemicals was everything. Whether the objects could fit together nicely was everything, right? So they were always in the habit of looking at things this way. And when the quantum mechanicists, when the mathematicians started talking about particles like electrons, the chemists said, oh, yeah, we've got those. That's the surface of the atom. And they're like, and the mathematicians are like, yeah, whatever. That's fine if you want to treat it that way. Cool. We don't need to do that because our equations work out either way. So the chemists, ever since the beginning of modern chemistry, have been really, really into the idea that material interactions are at the heart of everything. And so, yes, to answer your question, the electron in particular is a very abused word because the chemists use it to describe the surface of the atom. The particle physicists use it to describe an event with a particular amount of momentum that they can detect. And the chemists got cool with this. For shorthand, they'll talk about electrons being transferred here and there and whatever. But at the end of the day, the question is still begged, how is this motion of this event causing the propulsion of, you know, our lights right now? How is it that sending these little particles through a wire is able to turn the lights on, right? And the more chemically minded people would probably say, well, the atoms are doing something to one another all the way down the chain. There's some sort of transferred event. There's some momentum being transferred down that. Sort of like if I hit this table, actually the impulse is felt almost instantaneously at the other end of the table. Something like that going on, right? And the chemists have actually kind of been aware of this for a long time. Particle physicists are like, doesn't matter. As long as the balance of the equations is right at the end of the day and we can calculate how much power is getting to those, it's fine. Okay. Yeah. What's a neutrino? Yeah, that's a great question. Okay, so yeah, let's check out, hold on, before we get to the neutrino. So they what's that? Why is it uncertain? Okay, so, well, let's talk about masses in general, right? I touched on masses a little bit. Gosh, I'm going to run out of time here. These are important things, though, before. I don't think we can keep going with this class without setting out this groundwork stuff. Mass, what the heck does that word mean? Newton introduced it, right? He introduced it explicitly in the context of gravity. Now, the problem is, gravity is almost certainly an atomic process, right? Atoms undergo gravitational attraction to one another. I'm sticking to the floor right now. We're all sticking to the floor because the atoms of our body are interacting with the atoms of the earth in such a way that keeps us stuck to them. Now, this is all well and good, but how is it that we can describe the material of the atom, the electron, the proton, which is at the center? How can we describe those in terms of mass? Now, what they did, what the engineers of the time, the quantum mechanicists of the time did, was they made a really interesting leap of faith. And they said, okay, if we have an atom, we know how much it weighs, it's charged, and we put it in a magnetic field, then the amount that it's deflected by the magnetic field should be proportional to its mass, right? Which makes sense, you know. If I have something really heavy and I try to pick it up with a magnet, I'm not going to succeed. But if I have a strong enough magnet, in other words, and I can make electromagnets, so I can turn up the voltage on that thing until it can actually lift a car or something, right? The amounts of energy, electromagnetic energy, magnetic in particular, that I'm putting into that system is proportional to the mass in that sense, right? So we can make a conversion between mass and magnetism very easily. So when we see something like this, where we see a certain amount of mass, kilograms, assigned to a particle, what we're saying is actually this is the effective mass that would be ascribed to the deflection of this particle. And honestly, like that's God, we'll just get lost in the weeds if we try to unpack that too much. But needless to say, these are effective masses. They're conversions from deflection strength of different charges on atoms, right? Okay, so what is a neutrino? So these are the 4 players that we need to get through today in terms of what's happening in the sun. So, and maybe it's actually best to wait a second, but one of the things they realized very quickly about this fusion thing was that fusion released energy. There was some viable amount of effort that was released by cramming these atoms together. And it turns out that one of the types of energy that was released, well, there was a balance, right? So you could calculate that the charge was balanced at the end of the day. And that's how we get the electron contribution. This will all make sense more when we look at the reactions themselves in just a second. But something else happened too. There was a instance of radiation that occurred too, which was predicted in terms of the energy balance, right? There's a little bit of energy left over, which was assumed to be a radiation. And this is essentially the neutrino, right? So neutrino is a kind of radiation that's emitted. It's actually extraordinarily strong. And it's so strong that it seems to pass very quickly amongst groups of atoms. I think your textbook would say that it flies right through matter. I would say that it's actually relayed through matter very quickly, as if nothing was there. Now, we see this all the time, though, right? Light does go through matter, right? So a great example is a window, right? You can see through a window. And maybe another example, if that's not good enough, is how about your cell phones right now, or the Wi-Fi in this room, right? Those run on light, too. We generally don't always think of radio waves as light, but they are light. And so the particulars of how that relay is going on are another wide open topic for science, in my opinion, too, because it seems like the frequency of the light has everything to do with it. How big those waves are in terms of being able to excite groups of atoms so they can go through walls and things like this are really important. So the neutrino is a particular kind of light. It's very high energy, and it can be relayed through sets of atoms, no problem, which makes it very difficult to detect. And actually, the energy predictions that allowed us to even believe that this thing existed, or occurred, I guess is a better way of putting it, to believe that the neutrino occurred, were in place for tens of years. I don't know exactly, maybe 50 years before, maybe even, I don't know, maybe even 100 years, not quite, before anything approaching detection of these events was actually observed. And there's actually a nice little section in your textbook that describes the discovery of the neutrino, so check that out. But I want to make sure we make it through these nuclear reactions today, so I'm going to keep going. Okay, we talked about this. All right, so this binding energy. So these are the fusion reactions that we can expect in the sun. And I'm going to unpack each of them for you a little bit. But essentially the idea is that it takes a tremendous amount of energy to cram atoms together enough to get fusion of them together. In fact, we can calculate exactly how much energy, how much heat, or how much pressure is necessary. And this is what allows us, well, we know how much pressure is available in the sun because we know its density, we know its radius, and We know it's gravity because the planets go around it, right? So we can basically say how dense the sun is. We know how much pressure is at the center of the sun. It's not enough. And we also know that the only other contribution that would allow atoms to fuse together is temperature. They got to slam into each other really hard. And so this is what allows us to calculate and make statements about how hot the center of the sun is. That's really important in terms of us understanding the structure of the sun. So we can actually say, that something like 12 million Kelvin is required for this event to happen. So it's assumed that that's basically how hot it is down there, which is quite interesting. And this is these reactions are thought to be occurring deep inside the sun. Like, let's see here, something like 10% of the volume of the sun, like the inner 10% is where all of this is happening. So let's look at this chain of reactions. So something to keep in mind here. So the H is a hydrogen. That's that really simple spherical shelled atom. The He is helium, which of course the word helios comes from the Greek for sun. It was discovered in the sun. And yeah, that's all we need to worry about. We'll talk about the number signs in just a second. So this is a chain reaction. You basically have two hydrogens that get smashed together. They make a helium, they make a heavier hydrogen first. And this gives off an electron plus this little piece of radiation. There's another type of radiation. So this is our neutrino. Over here, we have this heavier hydrogen, which is getting smashed together with a lighter hydrogen. We get a heavier helium. The helium gives off a piece of gamma radiation, piece. See, look at me. It's not a piece of radiation, right? There's this event that's occurring. There's a radiation event. We call it gamma radiation. It's also very powerful and energetic. And then this heavy helium combines with another one, and we get an even heavier helium. And so this is sort of like a three-step reaction that's occurring. Now, it's very interesting because you'll notice that the biggest element that we're making here is helium, which is only step number 2 on the periodic table. Where the heck do the rest of the atoms come from, right? Because we have heavy stuff. I mean, these things, these metals, right? There's not enough temperature or pressure in the sun to make these. That's the idea anyways. And so where do they come from? And this is something akin to the crisis of how does the sun power itself. This is still a standing crisis in astrophysics, despite what people will tell you. Where do the heavy elements come from? Well, the thought right now is that they're produced during explosions, like giant explosions of stars, right, of these neutron stars. And this is certainly possible. There's some other possibilities too, which I hope to get to, but I don't think we'll have time, so we'll do them next class. But there's a new concept of fusion that's being investigated by NASA right now called lattice confinement fusion, which is quite fascinating too, where you can actually get squeezing you squeeze together different layers of material and you can actually fuse things as well without any of the temperature issues. Yes?
Aren't the heavier elements a byproduct of fusion going further than these 2 steps?
No. No, they're not actually. Well, they are, but they're not. They're in this explosive process in the destruction of stars. So they're not happening inside of stars. That's what's kind of interesting. So this is as far as it goes, actually. And so we have to have some other mechanism to generate the heavier things. The temperatures just aren't commensurate with fusion of bigger things, bigger elements,
I don't know if this is correct or not, but didn't like newer elements get made in also the birth of stars?
That's a good question. Not to my knowledge. To my knowledge, the standard explanation is that they're made in the destruction of these neutron stars. Now, you got to ask what a neutron star is at that point. We'll get to it, I promise. But needless to say, a neutron star is a little bit of a misleading word. It basically means that the things are crammed together so tight that they don't really have the same atomic structure that we think of. They're basically one giant fused thing in the first place. So it makes sense if you fuse all of your atoms together inside of these really dense bodies that when they come apart, maybe they'll come apart as bigger bubbles and smaller bubbles and everything else. Yeah?
I read something about the more smaller Berkeley.
I was just there.
What?
I was just there over break, yeah.
If anybody's been there, it's really cool.
It is cool.
They actually counted 3 or 4 different elements.
Right, so they can transiently produce some of these elements in the laboratory. That is interesting, right? So you can focus a great deal of energy into certain confined spaces and actually generate these. So artificially, you're right. But in terms of when we're thinking about where did all this iron come from, where did all of these heavy metals come from, where did uranium and plutonium come from, right? The thought is that these things couldn't have been done in a garden variety star. There must be some extenuating circumstances that allowed for their production. We'll deal with all of that, I promise. We're going to run out of time, and I want to make sure that we get through these 3 steps. So let's look at maybe a schematic of them. So the first thing that happens here, so actually that electron happens to have backwards spin to it, which is interesting. They call it a positron, right? So it essentially has all the characteristics of an electron, except it's charged oppositely. That's quite interesting. So that first reaction is not a true electron. It's what we call a positron. And actually, many of these, I would say almost all of these elementary particles, right, which we now understand are events, they have some corresponding version of themselves which are backwards. And that's quite interesting as well. So the first reaction you can see here, this first reaction gives off that neutrino, and it also gives off this backwards electron, which we call a positron. The heavier hydrogen here fuses together, so we get this production of this. So that heavier hydrogen, by the way, is called deuterium. You might see that sometimes. Those 2 are going to fuse together, and we're going to get our first helium, which is a helium-3. A little bit of mass is lost. Again, some materials, some mass, right? Because that's what's interesting about mass. Mass tells us how hard an atom can pull on another atom gravitationally. That's really what the word means. If you dig down to the bottom of it, what the heck does mass mean? Well, it's not necessary. I think it gets converted into the concept, again, because of the mistake with what a particle is, that mass tells you how much material is there. Well, indirectly, it sort of does for all of our purposes on Earth, right? But it also tells you something about what the material is like. And it turns out that these more complex atoms, we would call them heavier, which I think is totally reasonable. They are heavier. Does it mean that they're made out of more stuff? Probably, because they seem to be multiples of hydrogens. In other words, you got to stick hydrogens together in order to get a bigger atom, okay? But when we say that like mass is lost, this is very different from saying that material is lost at the atomic level. So we got to be careful with that. So in this case, some mass is lost and gamma radiation is emitted. So, you have some sort of energy conversion there when these bubbles get crammed together. Is material actually disappearing and turning into magic? I seriously doubt it. What I think is happening is that the material is getting crammed together and it's relaxing. The new bubble is a little bit more relaxed than the first one. Okay? So in this case, some gamma radiation is released as well. And then in our final step, we're creating helium-4. So helium-3 has got to combine with another helium-3. And what's interesting is that each one of these, this leads out with 2 more hydrogens, which are capable of going back and repeating the cycle. So this is a self-sustaining process. That's what's really cool about it. And that's why figuring out how to do this here is really important, right? Because it is, once you get this thing going, it keeps going. And it keeps giving off heat. It keeps giving off radiation. It keeps powering things, right? If we're going to travel to if we're going to leave this solar system, we got to figure out how to do this. If we're going to stop burning down our planet to stay warm, we got to do this. Most people on Earth still use wood to stay warm, okay? Yeah.
So is this the process used in nuclear power plants?
This is the ideal process used in fusion power plants. In nuclear power plants on Earth, we're actually tearing atoms apart. we're taking some of those really big ones that come from these processes, this neutron star process that I was talking about, or whatever. There's some other options too. We'll go into them at the beginning of class next time. But fission is when you rip atoms apart. It also releases energy when you rip the atoms apart, right? And you can get some of that back, and that's what we generally think of as nuclear power. But the word nuclear refers to either fusion or fission. Did everybody get the attendance sheet? Okay, sweet. Guys, let's put a pin in it today. Have a great rest of your week, and I will see you on Thursday. We'll continue the saga.